Good day. Welcome to the third lecture of metal forming. In the last two lectures, we discussed about the state of stress and the fundamentals of the plastic deformation, like the stress strain diagrams and different parameters which affect the plastic deformations, etc. So here in this lecture, we are going to discuss about the yield criteria. So that is actually the continuation of the second lecture. So in the last lecture, we discussed about the stress strain relationship. For any material, we can draw a stress strain relationship by conducting a UTM test. Okay, so for example, in this figure, here we can see a specimen is subjected to stress strain uniaxial tension, and the corresponding stress strain graph is drawn here. And here we can see the first specimen. It is loaded within elast limit. Okay, so this first specimen is loaded within elast limit. So after the removal of the load, what happened if the load is applied within elast limit? For example, this is my specimen. Okay, and I am applying a particular type of load. For example, I am applying a compressive force. Okay, in this I am applying a compressive force. When I release the load, and the load or stress which I applied on this member is within elast limit, or the stress applied is below that of the yield point of the material, what happened when I release the load, the material come back to its initial shape and size. Okay, when I release the load, the material come back to its initial shape and size. Okay, so that is up to this region. So this region actually belongs to the elastic region. Okay, so the first material, this one, so that is in the yield region or elastic region. Okay, it's not yield region, elastic region. Okay, next again I increase the stress value. When I increase the stress value beyond the yield point, what happened? When I increase the stress value beyond yield point, there will be some permanent deformation. So for example, here in this member, I am applying a load. For example, a tangential load is applied. Okay, so it is deformed like this. And after the removal of the load, there is no regain of shape and size. It is permanently deformed. So how this is permanently deformed? Here I am applying a stress which is greater than that of the yield strength of the material. Then only we got a permanent deformation. So here in the second figure, this is the second figure. The second figure, here the stress applied is greater than the yield point. Okay, this is the yield point. Greater than the yield point, the stress is applied. Okay, so when the stress is applied greater than the yield point, what happened? Or yield strength, then there will be a permanent deformation. The material will not come back to its initial shape and size. And again, the third region, that is necking. The necking, that means that is the ultimate point. Up to ultimate point, we can apply the stress. At that ultimate point, what happened? A necking will be developed on the material. This is the region of necking. See this, a localized deformation will be developed. Okay, for example, here in this specimen, when I apply the load, see this, in this point, a necking is developed. Okay, so after a particular, again, if I apply the load in this necking region, a fracture will be developed. Okay, a fracture will be developed. So this is a stress strain diagram we studied, and from the stress strain diagram, it is very easy to find the stress which is corresponding to the yielding. Okay, for any permanent deformation, we are studying about permanent deformation, because in metal forming we need a permanent deformation. After deforming the material to a particular product, that product will not come back to its initial shape and size. For example, I make a cup shape member using this. See this, I make a cup shaped member using the material. When I release a load, the member should not come back to its initial shape and size. That means we have to apply a load which is greater than that of the yield point of the material. Then only we got a permanent deformation. So in metal forming, for manufacturing any component, for example, if I want to manufacture this bottle, I have to apply the stress which is greater than that of the yield point of the material. Then only I got a permanent deformation. Okay, so in the simple tension test, here, how much amount of stress is required for permanent deformation? It is very easy. The stress applied should be, for example, if this is sigma y, yield point, sigma y, the stress should be greater than sigma y. The stress applied on the material should be greater than sigma y. Then only we got a permanent deformation. It is very easy. Okay, so that is in simple homogeneous uniaxial compression or tension, the metal flows plastically or permanent deformation when the stress reaches the value of the yield point or flow stress of the material. This is a material property. This yield point or yield strength is a material property. For plastic, it has a particular yield strength. For aluminum, it has a particular yield strength. For steel, it has a particular yield strength. So that is a material property. Okay. So if I may take a steel material for manufacturing this cup, for example, the yield point of the steel material is 200 gigapascal. Then I have to apply load or stress on this material greater than 200 gigapascal. Then only we can make a product by metal forming. Okay, so that is a material property. This yield point is the material property, or yield strength is a material property, and we know that by conducting different experiments we can calculate the yield strength of the material. By conducting universal tension testing, we can calculate the yield point of the material. Okay, so that is only for uniaxial stress condition. Uniaxial stress condition. So here in this case, if the load applied is greater than sigma y, we can surely say the material will plastically deform. It's very easy. But my question is that when I take another material, another component, which is subjected to combination of stresses. For example, here it is subjected to the sigma 1, sigma 2, this is sigma 1, and another one, sigma 3, okay, and this one, sigma 4. There are different types of stresses are acting. Combination of stresses are acting. See this. Combination of stresses are acting. Then, what is the stress required for plastic deformation? In a simple uniaxial case, we can directly say sigma y. This much amount of stress is required for plastic deformation. We can easily tell that. Okay, but for a system or for an object subjected to this type of combination of stresses, how much amount of stress has to apply for permanent deformation? This is a very important question. And the answer for this question is this yield criteria. Yield criteria. How much amount of stress is required for plastic deformation? And the answer for the question is yield criteria. So here in this lecture, we are going to study about this yield criteria. Okay, so this is the concept behind the yield criteria. So for a uniaxial tension case, we know if the force applied is equal to, this is F, okay, this is the F, and the cross section area is A. Then flow stress or yield stress is equal to force by area. Okay, and if the yield stress is if the material attain this yield stress, what happens? There will be a permanent deformation. Okay, and this is the flow stress is, and this is a true stress. Okay, not an engineer stress, this is a true stress. So what is yield criteria? Yield criteria is a law defining the limit of elasticity or the state of plastic deformation under any possible combination of stresses. For an object, for example, this is my object. Okay, it is subjected to different state of stress. See this sigma 1, sigma 2, sigma 3, sigma 4. It's a very complex state of stress condition. It's not a uniaxial tension test or uniaxial compression test. So here in this case, how much amount of stress has to apply? Is it sigma 1? Is sigma 1 is enough? Sigma 2 is enough? Sigma 3 is enough? Sigma 4 is enough? Or any other stress sigma has to apply for plastic deformation? We don't know how much amount of stress has to apply. So by applying this yield criteria or the law of yield criteria, we are going to study, or we are going to find out the stress required for the yielding or the permanent deformation of a material subjected to combined stress conditions or complex stress state. Okay, that is the essential content of this yield criteria. Okay, so here for an isentropic material, plastic yielding can depend only on the magnitude of principal stresses. I will explain what is that. There are various yield criteria has been proposed. You may study about the different theories of failure in the mechanics of solid class. Okay, there are 5 theories of failure. So in case of a structural member, actually the failure, we consider this as a failure when the stress developed on the material is greater than the yield point. So we consider that structure is under failure because there will be some permanent deformation. But in case of metal forming, we need permanent deformation. We have to apply a stress greater than that of the yield point of the material or yield strength of the material for permanent deformation. So here in this metal forming, the yield strength is the essential condition for plastic deformation. But in case of any structural member, if you take a structural member of the roof structure, in that case, amount of stress required for fracture is also can be explained using this yield criteria. So actually these both theories of failure and yield criteria are same. Okay, so in both cases we are finding the amount of stress required for this permanent deformation or plastic deformation. Okay, so basically there are two major yield criteria commonly used in the for defining in the theories of the plastic deformation. The first one is the Von Mises yield criteria. Von Mises yield criteria. This is very important yield criteria because in your higher semester you may use ANSYS software. Okay, so in the ANSYS software for the analysis of the structure we calculate the Von Mises stress. Von Mises stress. So here in this Von Mises yield criteria is used to find out the yield strength required for or yield stress required for plastic deformation. Okay, and that Von Mises yield criteria is basically about the distortion energy criteria. Another term is distortion energy criteria because this Von Mises yield criteria is developed based on the distortion energy. Yeah, I will explain what is that later. So that is the first yield criteria, Von Mises yield criteria. Second yield criteria is Tresca's or shear stress criteria. Tresca's yield criteria or maximum shear stress yield criteria. So in this lecture, we are going to study these two yield criteria, Tresca's yield criteria or maximum shear stress yield criteria. And the next one is Von Mises or maximum distortion energy yield criteria. Okay. So these two yield criteria are used to calculate the how much amount of stress or yield stress is required for plastic deformation of a material and which is subjected to combined state of stress. It's not a single uniaxial tension test. For a material which is subjected to uniaxial tension test, we can easily, from the stress strain diagram, we can easily tell the yield strength of the material can be calculated from the stress strain diagram. So this is the yield strength of the material. So this much of yield, if we cross the stress greater than that of the yield strength of the material, then that is the stress for the plastic deformation. We can easily calculate the yield strength from for a uniaxial tension test. But in this case, the material is subjected to or the object is subjected to a complex state of stress. In that condition, we have to use any of the yield criteria, either Von Mises yield criteria or Tresca's yield criteria to calculate the amount of stress required for plastic deformation. Okay. So first we are going to study about the Von Mises or distortion energy yield criteria. Okay. So here in this, we already discussed about these stress tensors. For example, a member subjected to complex loading condition sigma 1, sigma x, okay, in x direction, sigma y, okay, sigma z, etc. It's a complex loading condition, okay, and it may subject to some shear stress also, okay, this shear stress also. So I want to know the stress at a particular point, the state of stress at a point. Okay, I want to know the state of stress at this point. What is the state of stress at this point? Okay, how can we calculate? The state of stress at this point can be calculated. Through this point, we can draw number of lines, or sorry, number of planes with a different orientation. So there are number of planes with a different orientation. There are infinite number of planes. Okay, and out of this, I take 3 planes which are mutually perpendicular. 3 mutually perpendicular planes: x plane, y plane, and z plane. Okay, in that x plane, y plane, z plane, the stresses are sigma x, sigma y, sigma z are the normal stresses on the x, y, z plane, and tau x y, tau y x, tau z x are the shear stresses on the 3 mutually perpendicular plane. If we know these 9 stress components, then we can define the state of stress at this point. State of stress at this point using these 9 stress components, and these 9 stress components are arranged in a matrix, and that matrix is called stress tensor. Okay, so this is the stress tensor. Okay, stress tensor. So using this stress tensor, we can define the state of stress at a particular point. Okay, so here that is already we already studied in the mechanics of solids class, as well as in the last lectures also I explained this stress tensor. And this stress tensor, that is the stress tensor is used for this stress tensor is used for define the state of stress at a point. And this stress tensor can be divided into 2 parts. Okay, so the one part is called a hydrostatic pressure part. Okay, it can be divided into 2. So the one component is this one, hydrostatic pressure part, and the second part is this one, deviator part. Okay, by just by addition of this part and this part, we got this one, the stress tensor. Okay, so we just split into two parts. One part is called hydrostatic pressure part, and second part is called a deviator part. Okay, and in this hydrostatic component produces change in volume of the body, during the deformation. So here I am going to, this is my workpiece. I am applying a forging operation. Okay, this is a forging operation. I am applying a force F. I am applying a force F. A compressive force F is applied on this body. Okay, this is my body. Okay, or workpiece. And after forging, we got, this is the final body after forging operation. Its height is reduced. Okay, initial height was h, the final height was reduced to h1. Okay, so during this deformation, there will be some volume change. And this volume change is produced by this hydrostatic component. Okay, out of the total stresses we applied on the, so total stresses on a point is sigma ij. Okay, out of the total stresses on a point sigma ij, one part of the stress component, that is the hydrostatic component, is used for changing the volume of the component. Okay, this part is not used for changing the shape of the component. Actually, in the deformation, for the deformation, we have to change the shape. Okay, we have to change the shape. Then only we can deform a raw material into a particular product. Okay, but when we supply some amount of load on this member, out of the total load, one part is only utilized for changing the volume, and that part is called hydrostatic part. So this is the hydrostatic part, which is used for changing the volume. And we have another part, and that part is called deviator part, and this deviator part is contributed for the shape change. Okay, during the deformation of the raw material, we need to change the shape of the raw material. For the shape, when we supply some amount of load at a point on the raw material, sigma ij is the state of stress. Out of this sigma ij, one part which is called deviator part, this deviator part is used for the shape change. Okay, but the hydrostatic part is used only for the volume change. Okay, so actually we can say this deviator part is actually perform the shape change, or which is the usable part. Out of the total load applied, the usable part is the deviator part. Okay, so this is the deviator part. Deviator part is responsible for change in shape of the body. Hence, the yield function is a function of the component of this part of state of stress. Out of the total state of stress, this deviator part is responsible for shape change. Actually, during the deformation, we need shape change. We don't need any volume change. Okay, so this deviator part helps to change the shape of the component. So out of the total energy supplied, one part is used to change the volume of the material, called the volumetric or hydrostatic part, and the another part called the distort the shape of the, distort the shape, that means change the shape of the material. Okay, shape the change of the material, called the deviator part of the total stress on the particular point of the material. Okay, next, actually in the Von Mises stress, or Von Mises yield criteria, we only take this part, that is distortion or deviator part. So another names we can see distortion energy. Von Mises criteria, it has another name, distortion energy criteria. So actually, out of the total stress at a point, the deviator part is actually distort the shape of the, distortion means a change in shape, distort the shape of the component or raw material. So in Von Mises criteria, we take only the deviator part. Okay, we are not considering the hydrostatic parts in the Von Mises criteria. So according to Von Mises distortion energy criteria, a stressed metal body starts to yield or plastically deform when the relationship between the principal stresses and uniaxial yield strength sigma 0 of the material is sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equal to 2 sigma 0 square. So this is the Von Mises stress criteria definition. Von Mises stress criteria definition. So next time I will explain what is this definition. For example, I have a material. This is my material. Okay, this is an aluminum material. I conducted I apply stress on this uniaxial stress, uniaxial tensile stress is applied on this material. Next time I am going to draw a stress strain diagram based on the stress value. So I increase the stress value. Sorry, I increase the stress value from 0. Actually, for aluminum, the stress strain diagram may be vary. It's actually for my industry. Okay, so this is my yield point, sigma 0. I'm giving sigma 0. Okay, this is my yield point. So after this yield point, if the stress applied on this material is greater than the yield point, what happened? The permanent deformation will be developed. Okay, it will be a permanent deformation for this aluminum material. So in this uniaxial tension test, sigma 0 is the yield point. Okay, next I am taking the same material, aluminum material, okay, and it is subject to complex state of stress. For example, here in this direction sigma 1 is acting, here in this direction sigma 2 is acting, here also sigma 1, here a tau shear stress is acting, here a tau shear stress is acting, tau 1 shear stress. It's a complex state of condition. Okay, so in this complex state of condition, I take a point on this material. So this is my point on this material. Okay, in this point, we can calculate the principal stress values. Principal stress values are sigma 1, sigma 2, sigma 3. Sigma 1 is the major principal stress, sigma 3 is the minimum principal stress or minor principal stress, and sigma 2 is the intermediate principal stress values. On this point, how can we determine this principal stress? In the MOS class we studied how can we calculate the principal stress. For example, in this case, a sigma 1, sigma 2 in a plane stress condition. This is tau. Sorry. Okay, using more circle. Sigma 1. Sorry, this is tau. Sigma. Using more circle. Okay, we draw a more circle, and this distance is the sigma 1. Okay, that is the I'm sorry, here you may confuse with the letters. We can give sigma x. This is sigma x, this is sigma y. Okay, so here the conditions are this is sigma x, sigma y. Okay, otherwise you may confuse with these two types. So here the sigma x, this value is equal to sigma x, this much is the sigma x, this much is the sigma y, and the tau is the y direction. From this we can calculate the principal stress at that point. Okay, so similarly here in this case, in this body, this aluminum material, it is subjected to complex state of stress, and at this point the principal stress values we can calculate. Okay, sigma 1, sigma 2, sigma 3, that are the principal stresses on this complex state of condition. Okay, and in this sigma 1, sigma 2, sigma 3 values are the these terms sigma 1, sigma 2, sigma 3. Okay, in this yield criteria equation, these are the principal stress values at a particular point, sigma 1, sigma 2, sigma 3. And using this principal stress values, we got this equation sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equal to 2 sigma 0 square. What is the sigma 0? Sigma 0 is this one. Okay, so actually how actually in this Von Mises criteria, how we find this amount of stress required for this yielding? A body subject to sigma x, sigma y, tau 1, etc. like type of stress, and which produce a sigma 1, sigma 2, sigma 3 principal stress values. Okay, and based on the sigma 1, sigma 2, sigma 3 values, we write this equation. Okay, and the left hand side of this equation, if it is equal to 2 sigma 0 square value, what is the sigma 0? The yield strength corresponding to uniaxial tension or compression. The yield strength corresponding to uniaxial tension or compression. So if the left hand side values are equal to 2 into sigma 0 square, then there will be a yielding of the body, this body. Then there will be a yielding of the or permanent deformation of this body. If the left hand side is equal to or greater than, for example, we can give this also, not equal to alone, we can give greater than also, greater than or equal to, we can give greater than or equal to. That means at a body subjected to a complex loading condition, at a particular point, the principal stress values are sigma 1, sigma 2, sigma 3. Using sigma 1, sigma 2, sigma 3, we calculate the left hand side of the equation, that is sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 2, sigma 3 minus sigma 1 whole square. And that left side value of the equation is greater than that of the 2 into yield strength of the material in the uniaxial tensile test, 2 into yield strength square of the yield strength of the material in yield strength uniaxial test. Then we can say this object in the complex loading condition will plastically deform. It will plastically deform. For example, if another case, if it is less than, see this, we calculate sigma 1, sigma 2, sigma 3 principal stress values, and we calculate the left hand side of this equation. And if the value is less than the 2 sigma 0 square value, then there will not be yielding, there will not be any plastic deformation. After the removal of the load, the material, it has some complex loading condition. After the removal of the load, material regains to original shape and size. Okay, so this is the Von Mises criteria for plastic deformation. Okay, so actually nothing but this Von Mises criteria. The left hand side of this equation is the corresponding to complex loading condition. The right hand side of the equation is corresponding to the right hand side, this one 2 sigma 0 square is corresponding to uniaxial tension test. Okay, so actually using this Von Mises criteria, we combine this, or we develop a relation between these two, sigma 0 and the principal stress on a complex loading condition, and that relation is this equation. And if this equation is satisfied, greater than or equal to, if this equation is satisfied under complex loading condition for an object, then there will be permanent or plastic deformation. That is the condition for yielding. Okay, so this is called Von Mises or distortion energy criteria. So here we can give, instead of 2 sigma 0 square, we can give 6k square, out of k is equal to the tau 0, that is equal to sigma 0 by root 3. So we can directly, if k is equal to sigma 0 by 3 root 3, we can develop this equation also, 2 sigma 0 square. Okay, but this k is equal to sigma tau 0. That means if you draw same way, if you draw another graph, instead of the tension, instead of measuring the tension, we measure the shear stress, tensile stress, or normal stress, sigma. Instead of sigma, if you plot a graph between shear stress and shear strain, then the shear stress corresponding to yield point is called tau 0, and this tau 0 will be equal to k. So we can give this is equal to 6 tau 0 square. So this is the normal stress, sigma 0. If you plot the stress strain diagram with respect to normal stress and normal strain, then we got the right hand side 2 sigma 0 square. If you plot a stress strain diagram with the shear stress and shear strain, then the shear stress value is equal to, we give 6 tau 0 square. Both equations are same. So this is the condition for yielding based on the Von Mises stress criteria. This is very important yield criteria, commonly used in most commonly used in engineering application for the analysis of the metal forming process. So next yield criteria is Tresca or maximum shear stress criteria of yielding or plastic flow. Next, we already discussed the Von Mises yield criteria, which is based on the distortion energy. We can divide into or separate into two parts, deviator part or distortion energy part. And using the distortion energy part, we develop the Von Mises criteria. But in this case, Tresca's criteria, that is based on the maximum shear stress. Okay, maximum shear stress. So how it is defined? A metal body reaches the yield point or reaches a permanent deformation when maximum shear stress in the body reaches the values equal to the yield strength of the metal in shear. Okay, so the similar to the previous case, here also we can explain. Consider an aluminum member is subjected to, here I am applying pure shear. Okay, instead of applying shear tensor stress, I am applying shear stress. The tau is the shear stress applied on this aluminum member. And using this application of shear stress also, we can plot the stress strain diagram. Okay, so this is the shear stress. This is the shear strain. Okay, and for example, this is the stress strain diagram corresponding to shear stress and shear stress. It's not normal stress and normal strain. Here we increase the shear stress on this aluminum member. And in this, so this is the shear stress. And at this point, the shear stress value equal to tau 0. That is the shear stress corresponding to yielding. Okay, if the shear stress is greater than sigma 0, tau 0, then there will be a permanent deformation of this material. So this is a simple case, and using this simple case we can do the experiment and we can calculate the shear stress required for the plastic deformation, or the shear stress corresponding to yield point for the aluminum material. Okay, and from the data book also we can determine this value. By conducting the experiment we already calculate this value tau 0 for the aluminum material. Next one is here the same aluminum material. We take the same aluminum material. It is subjected to complex state of stress. For example, this is sigma y, sigma x, tau. This is tau. This is sigma y, sigma x. Okay, it's complex state of stress condition. I want to calculate, similar to the previous case, I want to calculate the state of stress at this point. State of stress at this point. What we do? We calculate the principal stress values. Principal stress values are sigma 1, sigma 2, sigma 3 principal stress values. Okay. And for example, this is a plane stress condition. So in the plane stress condition, we have only sigma 2 and sigma 3. Okay. So here, once again, I'll explain with a plane stress condition, then it will be more clear. So this is my aluminum body. This is sigma x, sigma y, sigma x, tau. So plane stress condition. You know how to draw a Mohr circle based on this plane stress condition. In this Mohr circle we have, this is sigma, in this direction sigma, in this direction tau. Okay, and initially we have sigma x. This much is sigma x. This much is sigma x. This much is sigma y. Okay, and tau is also acting. So this much is tau. Tau is this much, and this much is tau. So how we draw? We draw a line like this. Then we draw a circle passing through this. Okay, we draw a circle like this. Then from this circle, what is this value? This value? What is this value? That is a sigma 1. And what is this value? This is sigma 2. That is sigma 1 and sigma 2 are nothing but sigma 1 and sigma 2 are principal stresses. You know, from the Mohr circle we can draw this, we can calculate the sigma 1, sigma 2. Okay, and the next question is this one. What is the maximum shear stress at a particular point? Sorry, in this object, the maximum shear stress is this much. This is also, you know, this is the maximum shear stress. That means this value. This is the maximum shear stress. Tau maximum. What is the relation between tau maximum and the sigma 1, sigma 2? Tau maximum equal to, that is actually the radius of the Mohr circle. That is equal to sigma 1 minus sigma 2 by 2. Actually, this is radius. And sigma 1 minus sigma 2 is this much. Diameter of the Mohr circle. Diameter of the Mohr circle divided by 2 is the radius, that is equal to tau max. So maximum here in this body, the tau maximum shear stress developed on this under this complex loading condition is equal to sigma 1 minus sigma 2 by 2. That is the difference of half of the difference between the principal stress values. Okay. So in this complex loading condition, maximum shear stress is equal to tau maximum. Okay. And if the same material, for example, this is aluminum material, same material subjected to pure shear, from the stress strain diagram we got the amount of stress required for plastic deformation is tau 0. Then how this material or how this object deformed, how much amount of stress is required for deformation, and the amount of stress required for the deformation is explained with the Tresca criteria. So if tau max developed on this complex loading condition is greater than or equal to the amount of shear stress corresponding to yield point, then there will be a plastic deformation. This is the Tresca criteria. Okay, so for a body, for a material, the tau zero is the shear stress corresponding to yield point. Okay, if we apply the shear stress greater than tau zero, then there will be a plastic deformation for that material. So tau zero is the minimum amount of shear stress required for plastic deformation of a material, tau zero. And we take an object which is subjected to complex loading condition, and in that object the maximum shear stress is equal to tau max, which is equal to tau max. And what is the condition for the plastic deformation, permanent deformation of the object under complex loading condition? Under complex loading condition, some amount of shear stress is developed, that is a maximum shear stress developed on the body is tau max. If tau max is greater than tau zero, then there will be a plastic deformation for the material under complex loading condition. So this is the condition for Tresca criteria for plastic deformation. Okay, so we can write tau max is equal to, tau max we already written that as sigma 1 minus sigma 2 by 2. Okay, which is greater than or equal to tau zero, greater than or equal to tau zero, then there will be a permanent deformation or plastic deformation. Okay, so this is the case of this one. This is the case of plane stress condition for explaining how this Mohr circle. We can draw the Mohr circle in the 3-dimension also. This is a 2-dimensional Mohr circle. We can draw the 3-dimensional Mohr circle also, but you may not familiar with the 3-dimensional Mohr circle. That is why I explained how this tau max is equal to T and sigma 1 minus sigma 2 by 2 using a 2-dimensional or plane stress Mohr circle condition. So if we draw a 3-dimensional Mohr circle, we got 3 tau maximum. Here we have only 1 tau maximum. So 3 tau maximum are tau 1 maximum, that is sigma 1 minus sigma 2 divided by 2. That is already I explained using this 2-dimensional Mohr circle. Similarly, we have another tau 2 maximum, that is half of sigma 2 minus sigma 3. Sigma 2 and sigma 3 also a principal stress value. Sigma 1 is the major principal stress, sigma 3 is the minor principal stress, and sigma 2 is the intermediate principal stress. And sigma 3 is another maximum shear stress, that is equal to half of sigma 3 minus sigma 1. And out of this, if in this if we take this one in this order, if the shear principal stress values are in this order, sigma 1 is greater than sigma 2 greater than sigma 3, then of course the maximum shear stress will be sigma 1 minus sigma 3. Sorry, maximum shear stress will be sigma 1 minus sigma 3. Okay, that is the maximum shear stress. And if it is greater than maximum shear stress on the complex loading condition greater than or equal to the shear stress corresponding to yield point, then there will be a permanent deformation. So we have to apply a complex loading condition such that correspondingly a tau max will be developed, and that tau max should be greater than that of the shear stress corresponding to yield point of the material. Then there will be a permanent deformation. Okay. Next, I will explain how this yield criteria will applicable for a metal forming process. Okay. So here, for example, I am doing a forging operation. This is my workpiece. I am going to deform using a die. I am applying a force here also using another in order to prevent barreling. Okay, in order to prevent barreling, I am applying a force also in the tangent or transverse direction also. A force is applied here in this direction. A force is applied in this direction. Okay, sorry, in this direction. Okay, then there will be some shear stress between the die and the workpiece. There will be some shear stress here. Here also there will be some shear stress. This is a complex loading condition. Okay, it's a complex loading condition. This is F1, this is F2, this is tau 1. I don't know what is F1, how much amount of force has to apply. For example, this is aluminum material. I want to find the F1 value, F2 value, this tau 1 value. I need a permanent deformation. During forging operation, I need a permanent deformation. So what will be F1, F2 and tau 1 value? So to calculate these 3 values, how much amount of load has to apply for permanent deformation? For that, what we do? We first analyze this loading condition. Okay, we take the body, free body diagram, F1, F2, shear stress, And by after analyzing, we got three principal stress values: sigma 1, sigma 2, sigma 3. Okay. And out of this, from this sigma 1, sigma 2, sigma 3, using this formula, sigma 1 is greater than, in this three principal stress values, sigma 1 is greater than sigma 2 greater than sigma 3. Okay. So we can use this formula. Half of sigma 1 minus sigma 3 is the maximum shear stress on this body. On this body, maximum shear stress will be this. Using this formula, we can calculate. Then, what is the essential condition? We know for aluminum material, the tau 0 is the amount of shear stress required for plastic deformation in under pure shear condition, tau 0. So, just check whether tau 0, this tau max is greater than or equal to tau 0. Tau max is equal to half of sigma 1 minus sigma 3. Tau 0 is available from data book for aluminum material. What is tau 0? That is available from data book. Just to check this, whether this left hand side, half of sigma 1 minus sigma 3, or tau max is greater than or equal to tau 0. If it is greater, then there will be a plastic deformation. From that, we can calculate F1 and F2 and tau 1. Okay, we give some values 10, 10, 5. Using 10, 10, 5, we calculate sigma 1, sigma 2, sigma 3. Based on we calculate tau maximum. And if tau maximum is greater than tau 0, then we can use 10, 10, 5 values for plastic deformation. And if you use 5, 5, 5, 3, 2 values, 5 Newton, 3 Newton, 2 Newton. Okay, and then I analyze sigma 1, sigma 2, sigma 3. We got a different sigma 1, sigma 2, sigma 3 value. Using that, I calculate tau maximum. If the tau maximum is less than tau 0, then these 5, 3, 2 loads are not enough for plastic deformation. So that is the use of these criteria in the metal forming area. Okay. So that is the Tresca's criteria. So here Tresca criteria is based on the maximum shear stress. How much amount of shear stress is required for plastic deformation. So I already explained this Mohr circle. So actually, in this, from this Mohr circle, it's clear. For example, I take a sigma 1. Sigma 1 is only uniaxial tension. So here we can draw a Mohr circle. So sigma 1, that is sigma 1. This much is sigma 1. Sigma 2 equal to 0. Sigma 2 equal to 0. Okay. So there is no sigma 2. So we can draw shear stress also equal to 0. Okay. So we can draw a Mohr circle like this. And in this, from this we got tau 0 equal to sigma 0 by 2. Sigma 0 by 2. That is half of the principal stress. If it is a only single normal stress is acting, then it will be sigma 0 by 2. And that is also already explained. That is sigma 1 minus sigma 2 by 2 is equal to this tau maximum. Tau maximum equal to sigma 0 by 2. Okay. So this is the Tresca criteria. So we discussed two criteria. First one is Von Mises criteria. In that also we have one equation, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 2 sigma 0 square. So under complex loading condition, if the equation is satisfied, then there will be a permanent deformation. And the Tresca criteria is based on the maximum shear stress. And sigma 1 minus sigma 3 whole square by 2 is, sigma 1 minus sigma, not whole square, sigma 1 minus sigma 3 by 2 is the maximum shear stress. And on a material, the maximum shear stress crosses the shear stress corresponding to yield point of the material, then there will be a plastic deformation. That is the Tresca criteria. Next, we are going to compare these two criteria, yield criteria and Tresca criteria. And we have two criteria. We don't know. I take aluminum material, so I have two criteria. Using two criteria, I got two data. So I have to decide which criteria is more suitable for that material, for aluminum material. For that, scientists conducted different experiments, and based on the experiments, they concluded that for the ductile material like aluminum, copper, etc., the Von Mises criteria is more suitable for this type of ductile material. Okay, Von Mises criteria is more suitable. But so that is calculated using this plane stress condition using a thin-walled tube. But however, the use of Tresca criteria is found results is negligible difference between two criteria. So when we it is not wrong, we use Tresca criteria for ductile material. the result between this Von Mises criteria and the Tresca criteria for ductile material is somewhat very negligible. It's very small. So we can use either Tresca or Von Mises criteria for ductile material, but in different applications we commonly see Von Mises criteria is commonly used for this ductile material. Okay, so the comparison of Tresca and Von Mises criteria can be expressed by superimposing the elliptical yield locus Von Mises and the hexagonal yield locus Tresca together as shown in the figure. So next we are going to compare these two criteria. Okay, so we already discussed this equation. This is for Von Mises criteria. Using this equation is actually representing a cylinder. This is the equation of a cylinder. So using this equation we can draw a cylinder. Okay, so we can draw a cylinder like this using this equation. Okay, in x, y, z direction. This is sigma 2, sigma 3, sigma 1. That is the principal stress values. Okay, and we can check whether a body plastically deform or not under a particular state of stress using this diagram. So initially draw a cylindrical surface using this Von Mises criteria equation, and material will suffer plastic deformation when the state of stress at that point is on the surface of the cylinder and the stress increment is directed outside the cylinder. Okay, so this is very important. For example, I am taking a body with a complex loading condition. If the state of stress on this body is within the cylinder, then we can say the material will not plastically deform. Okay, there will not be any plastic deformation. Then what is the state of stress corresponding to plastic deformation? The state of stress corresponding to plastic deformation when the state of stress of this body is on the surface and it is directed outside the surface of the cylinder. Okay, if the state of stress represented on a body is on the surface of the Von Mises cylinder and it is directed outside of the cylinder, then we can say there will be a plastic deformation or permanent deformation for that body under the complex loading condition. But inside this cylinder, it is a safe region. There will not be any plastic deformation. But in case of metal forming, we have to apply stress or a combination of stress such that the state of stress should be in the surface or it is in the outside, directed towards the outside of the cylinder. Then only a plastic deformation will be developed. Okay, that is the case of this Von Mises criteria. And similarly, we can draw a diagram for Tresca criteria also. In case of Tresca criteria, we only studied the simple equation, that is sigma 1 minus sigma 3 by 2 is equal to tau 0. Okay, that is a simple equation. But in case of Tresca criteria also, we can develop a generalized equation. Here I am not actually discussing about this generalized equation, but there is a generalized equation for Tresca criteria like similar to this Von Mises criteria, and using that generalized equation representing a hexagonal prism. Okay, so this Von Mises criteria representing a cylinder, but the Tresca criteria representing a hexagonal prism. So we can draw a hexagonal prism on a based on the Tresca criteria. In this stress system diagram. Okay. The similar concept is also applicable for Tresca criteria. If the state of stress on a particular body, if it is inside this hexagonal prism, then there will not be any plastic deformation. But if the state of stress is on the surface and if it is directed outside of the surface, the state of stress is directed outside of the surface of the hexagonal prism, then there will be a permanent deformation. So this is the essential condition for the permanent deformation of the body. So that is the hexagonal prism. We can superimpose this Tresca criteria hexagonal prism under this Von Mises criteria cylinder. See, here we can see the superimposition. When we superimpose, we can see actually the hexagonal prism inscribed on the, see this, the hexagonal prism. This is a hexagonal prism. The hexagonal prism inscribed on the cylinder. That means this area, see this area, in between the hexagonal prism and the cylindrical Von Mises cylinder, there is some area. So that in that, if the stress system is in that area, then According to Tresca criteria, there will be a plastic deformation, but according to Von Mises criteria, there will not be any plastic deformation. But that gap between the hexagonal prism and the cylinder is very small, so we can approximate both the Tresca and this Von Mises criteria is applicable for all materials. Okay. So this is the this is the area gap area I mentioned. If the stator stress is in this gap area, then it will not obey, or there will not be any plastic deformation according to Tresca criteria, but there will be some plastic deformation according to Von Mises criteria. So this is actually the picture showing the superposition of the Von Mises cylinder and the Tresca's hexagonal prism. And if it is, we can convert, here it is a three-dimensional sigma 1, sigma 2 and sigma 3, three-dimensional stress system. We can convert into a plane stress condition. When we convert this into plane stress condition, the cylinder converted to the cylinder, that means that Von Mises cylinder converted to ellipse, an ellipse, it is converted to an ellipse. If we consider the plane stress condition, that means sigma 3 is equal to 0, there is only one sigma 1 and sigma 2. Okay, then the cylinder converted to ellipse, and in that ellipse, this is the sigma y, that is the yield point, yield strength corresponding to uniaxial tension or compression test. Okay, and if we consider the plane stress condition for the Tresca criteria, this is for Von Mises cylinder, this is for Von Mises cylinder in plane stress condition, and this is for Tresca's criteria. Okay, this is for Tresca's criteria in plane stress condition. Okay, and this cylinder in Tresca criteria, here it is a hexagonal prism. It is converted to a hexagonal shape. So this is a hexagonal shape object. Okay, so here also we can, in 2 dimension also we can inscribe this Tresca's Von Mises ellipse, and we can see the Tresca's hexagon. This is the Tresca's hexagon. Okay, this is the hexagon. We convert this, when convert the prism, hexagonal prism, into 2-dimensional or plane stress condition, it is say Tresca's hexagon. So we can inscribe these two, hexagon and ellipse. We got this image, and this is a so this is the another image showing, actually this is according to the theories of failure. This is actually the region where, that means inside of this region, inside of this hexagon or the ellipse, that is a safe region without any plastic deformation. But in case of metal forming, the state of stress should be outside of these two ellipse and hexagon. Then only there will be a plastic deformation. Okay, and this is according to distortion energy. The ellipse is based on the Von Mises criteria, and according to maximum shear stress or Tresca criteria, we have a hexagon. And here the sigma 1, sigma 3, both are tensile is acting. This is the ellipse. Okay, and here this region, the first coordinate region representing a biaxial stretching in both direction, in the sigma 1, that means sigma 2 equal to 0, sigma 1 has only value, that is a uniaxial tension test, and this region, that is actually a compression, this sigma compression region, and this is the plane straight deformation region, this region, and this is a pure shear region. Okay, so you have to remember this. According to Von Mises criteria, we have an ellipse in plane stress condition and a hexagon for Tresca criteria. Okay, and when we inscribe this hexagon in an ellipse, we got a region where plastic deformation occur and a region where elastic deformation occur. Okay, so region outside of this ellipse is the region where plastic deformation occur. So the stress system, if you take a body subjected to complex loading condition, the state of stress should be outside of this ellipse and hexagon for plastic deformation. If it is inside, it is only a elastic deformation. So that is about the yield criteria. So we have two yield criteria, Von Mises and Tresca's yield criteria. Next this is floor rules, that is actually a continuation of the yield criteria. When the stresses at a given point in the metal reaches certain level, okay, So stresses at a given point reaches a certain level as specified by the Tresca criteria and Von Mises criteria, then there will be a plastic deformation. Okay, so that certain level, what is the level in case of Tresca criteria? The level is the maximum shear stress corresponding to yield point. That is the level. Okay, so in Tresca criteria, the stresses at a point reaches the shear stress corresponding to yield point of the material, then there will be plastic deformation. But in case of Von Mises criteria, what is that certain level? In Von Mises criteria, the equation, the left hand side of the equation reaches the 2 times of the square of the yield point corresponding to uniaxial tension or compression. Then there will be a plastic deformation. These are the 2 levels. So here, in case of in the stress strain diagram, we know the equation up to this point. In this region, up to yield point or elastic limit, we know stress is directly proportional to strain, or stress is equal to strain in Young's modulus into strain. That is Hooke's law, generalized Hooke's law or Hooke's law. Okay, but is there an equation in this region? This is the region of elastic. This is the elastic region. This is the plastic region. Okay, so in this plastic region also there are some relationships, and that relation is this one. These are the relationship in the plastic region. So similar to the Hooke's law, which gives the relationship between the state of stress corresponding to deformation in the elastic region, analysis of the plastic deformation requires certain relationship based on the applied stress and the corresponding strain. Here in the elastic region, we have a relation between stress and strain. But in case of plastic region, we have the relationship between stress and not strain. It is strain rate. It is not strain, it is strain rate. We already discussed strain rate. What is the amount of strain with respect to time? How much, for example, in case of hammering, the strain rate is very huge. Because with respect to time, very small time, we apply huge strain by hammering. So we can say strain rate is very high. But in case of very small, low speed pressing operation for deformation, the strain rate is low. What is the reason? With respect to time, the amount of strain induced on the material is very low. Okay, so that is strain rate. So here in this plastic region, the relationship between stress and strain rate is expressed by these 3 equations. So the strain rate, this is strain rate. We represent strain rate with the epsilon dot. So strain rate in one direction is equal to lambda into sigma 1 minus sigma m, where sigma m is the mean stress. Sigma 1, sigma 2, sigma 3 are the principal stress values. These are the principal stress values, sigma 1, sigma 2, sigma 3. And the mean stress is equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So here sigma m is the mean stress, sigma 1 is the principal stress in the one direction. So lambda into sigma 1 minus sigma m is the strain rate in the plastic region. And sigma 2 dot is equal to epsilon dot 2 dot is equal to lambda into sigma 2 minus sigma m. Epsilon dot 3 is equal to lambda into sigma 3 minus sigma m. And this is the equations of plasticity or flow rule. This is called flow rule. Okay, so in the floor region or plastic region, this is the region of plasticity, plastic deformation. So in the plastic region, this is the elastic region where Hooke's law is applicable. But in the plastic region, we use this equation, plasticity equations. And here in this lambda, that is dependent upon the direction of plastic flow, temperature, material, strain rate, etc. Different factors are affecting this lambda, that is a constant value. Next, we are going to study about the power and the energy required for deformation. How much amount of power and energy required? For example, take the case of a forging operation. Here I am applying a force F. Okay, so similar body is shown here. The body is subjected to plastic deformation. How much amount of power and how much amount of load is required for the plastic deformation? Actually, when we apply when we do a plastic deformation, that is irreversible. That means we supply some mechanical energy. This is a mechanical energy. The force is applied in the form of mechanical energy. And when we apply the mechanical energy on this workpiece, the workpiece is deformed. Okay, but this is a plastic deformation. This is not an elastic deformation. So this is irreversible. We cannot reverse this because already the material is plastically deformed. So the mechanical energy consumed during deformation is transformed into heat. So for example, if we supply 100% of mechanical energy, around 95% of mechanical energy is used during the deformation is converted to heat. Okay, so during the plastic deformation, huge amount of heat is developed. And what is the source of that heat? The mechanical energy which is supplied is utilized for converting into heat, and that is actually transmitted into atmosphere or conducted to the die, etc. Okay, so here in this we can develop a relationship for homogeneous plastic deformation. Take this object which is subjected to plastic deformation. Here, this is sigma 1 into W into L. So here it has a width of W and length of L and height of H. This is the different parameters of this object. And here the force applied, force we know, force by area is equal to stress. So stress into area equal to force. So here stress is equal to sigma 1 into area is equal to W into L. So the force in this direction is equal to sigma 1 into W into L. In this direction, force is equal to sigma 2 into H into L, because here the area is equal to H into L, cross-section area. So similarly, in different directions, we can calculate the force in different directions. Okay, so that is actually shown here in this figure. And here in this, we can calculate the strain in the one direction. What is the one direction? This is the one direction, direction 1. The strain in the direction 1 is equal to natural logarithm log h by h0. So we already studied the true strain. We already studied that. See this one. So the true strain is equal to log L1 by L0. True strain. That is equal to so log L1 by L0. That here the initial length is this one, and the final length is this one. Log L1 by L0. So using this equation, we can calculate here. So here epsilon 1, the strain in the one direction is equal to log h by h0. And here in the previous case, the strain rate, that is equal to V by H. Strain rate is equal to V by H. That is also we calculated. What is the strain rate? The last lecture I explained that. V by H. Strain rate is equal to dou epsilon x by dou t. From this we got dou Vx by dou x. Dou Vx by, that means the change in velocity with respect to the distance. That is the strain rate. So similar strain rate also can be applied in this equation. In this case, strain rate is equal to Vh by H. In the H direction, this is the H direction, H. So H by initial H by H0, log H by H0 is the strain, and true strain, and strain rate is equal to V by H. Similarly, in the two direction, epsilon 2 is equal to that. What is the two direction? This is the two direction. We can calculate in the two direction we have W by W0. So VW by W. In the three direction, what is the, which one is the three direction? This is the three direction. See this, three direction. In this direction we have L, log natural logarithm L by L0. Okay, so we can calculate the strain and the strain rate. So here power is equal to, what is the power? Power is equal to force into, we can give velocity. Okay, force into velocity. So which is equal to total power is equal to the deformation, that total power requirement for the deformation is equal to power for the material flow in the one direction, power for the material flow in the two direction, power for the material flow in the three direction. That is equal to total power is equal to in the one direction F1 V1 plus this is the amount of power required in the one direction for the material flow. For two direction F2 V2, for three direction F3 V3. And here F1 we can give sigma 1 into area. Area is equal to, in one direction what is the area? In one direction area is equal to W into L. So W into L into, in one direction what is the velocity? Is equal to Vh. Similarly, in the two direction we can write the F2 V2. We can write F2 V2 like this. We can write F3 V3 like this. So we got total power. After simplifying, we got here in this, we got this Vh from the previous example. What is strain into H is equal to Vh. So we can substitute that here. Instead of Vh, we can give H into strain rate. From this, we got this equation. This is the power requirement for the plastic deformation. Okay. So sigma 1, sigma 2, sigma 3 are the principal stress values. Epsilon 1, epsilon 2 dot, epsilon 3 dot are the strain rates in the 1, 2, 3 direction. P is the volume. V is the volume. Okay. So similarly, we can calculate the strain in another times. These are the two equations in the another times. So this is the equation to calculate the power and energy for deformation. The last topic is the heat generation and heat transfer in metal forming process. So in metal forming process, commonly we do metal forming by two way, that is hot forming and cold forming. here in this picture we can see this is the material is in a very hot condition. Okay, so we can say this is a hot forming or warm forming. And in some case, we do the forming operation for a cold room temperature. The material will be in the room temperature. And that type of forming is called a cold forming. Okay. And here in this forming process, during the deformation, actually we apply the, in this direction, we apply the force or mechanical energy is applied in this direction. When we apply the mechanical energy, out of the 100% of mechanical energy we supplied, 95% of the mechanical energy during the plastic deformation converted into heat. It is converted into heat. So the heat will be developed in this region. In this region, very huge heat is developed. So how this heat is transferred? What are the different modes of transfer of the heat? After the total heat generated, some percentage of the heat remain in this deformed material. So some percentage of heat is remain in the deformed material. Some percentage of heat is transferred into the die from the deformed material. The generated heat is particular percentage of heat is transferred into the die, and some amount of heat is transferred into the die, upper and or male and female die. Some amount of heat is transferred to the atmosphere in the form of radiation. In the form of radiation, it is transferred. Okay, so these are the different heat transfer during the deformation process. And one more source is there. One main source of the heat generation is friction. There will be a friction between the die and the workpiece. During the plastic deformation, there will be some expansion and a contraction. So there will be a sliding between the workpiece and die. And this sliding generate heat, frictional heat. That is also a source of heat during the metal forming. Okay, so we can use lubrications, etc. to reduce the heat developed in the deformation zone. And this heat development affect the tool life. The die life will decrease by, and it also affect the microstructural properties of the forged parts. So we have to control the heat generated during the metal forming process. See this is the forging operation. So here we can see this. There is a movement in this direction. There is a movement of workpiece in this direction. See this. Okay, so this movement actually develop a friction between the workpiece and the surface. And that friction also is a main source of heat generation in metal forming. So we have to control that also. Okay, so let's next we can see what are the different sources of heat. Okay, so first source is the initial temperature of the workpiece. In case of hot forming, we heat the material into very hot condition before forming operation. For example, in case of blacksmith, before hammering, blacksmith is actually heating the material to very hot condition. So there will be some temperature or heat on a workpiece for forming, before forming. And heat generation during plastic deformation and between the friction and workpiece die interface also a reason for heat generation. So by the plastic deformation, the mechanical energy which we supplied, here we apply the mechanical energy. We apply the mechanical energy for plastic deformation. So most of 95% of the mechanical energy used for the generation of heat. So that is the source of heat. Another one, the friction between the workpiece and the die. Because of the relative movement between or sliding between the workpiece and the die, a friction will be developed. And this friction generates heat. That is also a source of heat. Another one is the heat transfer between the workpiece and die, between the workpiece and environment. So these are the two sources of heat, main sources of heat. Okay, and the generated heat, how this generated heat is transferred to environment and transferred to die. So this generated heat may transfer to die because die is cold, but workpiece is very hot. So there is a chance for the transfer of heat from the die workpiece to die. And another one is the transfer of heat from the workpiece to atmosphere. From workpiece to atmosphere, but in terms of radiation, etc., or by means of convection, etc., the heat is transferred to atmosphere. So these are the different heat transfer in the or heat generation in the case of metal forming. So we can conclude total heat change or temperature change during the metal forming is equal to QW plus QD plus QF minus QT minus QR plus Q minus QC. So these are the heat generation. These are the heat dissipation. Okay, these are the terms which is used to represent the heat dissipation. This is the terms which is used to represent the heat generation. What is QW? Initial work temperature. Some heat is already in the initial workpiece. That is QW. QD, that temperature increase due to plastic deformation. Mechanical energy converted to this heat energy during plastic deformation. That is QD. That is also increase the temperature. QF, that is the frictional heat between the workpiece and the die. There will be some friction that is also develop a heat. So these are the three reasons for the heat generation. How this generated heat is dissipated? QT, that is the temperature drop due to the heat transfer into the die. From the workpiece to die. Die is a very cold object. So hot workpiece, from the hot workpiece, the heat is transferred to the die. QT, that is QT. QR is the temperature due to drop due to radiation. By means of radiation to the atmosphere, there will be a reduction in the temperature. QC is the temperature due to drop due to convection. So here we have around the workpiece we have air. Around the workpiece we have air. So there will be some heat transfer by convection from workpiece to air. So these are the different modes of heat transfer in the metal forming operation. Okay. So this heat transfer due to this QD, theta D, that is due to plastic deformation. Which for that we have an equation. So don't need to study this equation. Just for the information, I put it in the slide. And this is directly proportional to the area. Sorry, A is the convection factor. Sigma dash is the average flow stress, average strain rate, time of contact. That is also important. Time of contact. C and P are the specific heat and specific weight, etc. And beta is the energy transformation factor. So here these are the different factors which affect the increase of the heat during the deformation. Another equation is the heat generation due to friction. There will be sliding between the workpiece and the die, which increase the frictional heat. And these are the different factors. You just read these factors also. The last topic is the temperature in forging operation. So I already explained what are the different sources of heat in the forging operation. We can classify the forging into two: cold forging and hot forging. And this is an example for hot forging. Here we can see the workpiece in the very hot condition. That is the hot forging. But we can use cold object also. The object temperature will be room temperature. That also we can use. But at that time, for metal flow or plastic deformation, we have to apply a huge amount of load in case of cold deformation. So we can do deformation or forging in by means of cold forging or hot forging. So here in this, when we increase the temperature, what happened? Blacksmith commonly heat the workpiece before hammering. So what is the advantage of heating the workpiece? When we heat the workpiece, we can deform the material with a very low load. Okay, the hammering load is very low. Requirement is very low when we heat the workpiece. But if we hammer a cold object, then we need to apply more amount of load for deformation. So this temperature is a big factor during metal deformation or metal flowing. So the yield strength is the important factor. Yield strength, and if we can reduce the yield strength, for example, we reduce the yield strength from here to here. Here this much is the yield strength, but here this much is the yield strength. By some means, if we can reduce the yield strength of the material, then we can easily deform, because plastic deformation occurs when we apply a stress greater than yield stress of the material. So the important technique or main technique for reducing the yield strength is temperature. Just to increase the temperature, we can reduce the yield strength. Thereby, we can easily do plastic deformation of the metal. Okay, so by reducing the temperature, actually the ductility also increased. So that is the first technique to or the influence of the temperature and the heat for deformation. If you reduce the temperature, if you increase the temperature, we can reduce the yield strength of the material. Thereby, we can easily perform the metal forming operation. Another important factor is the strain rate. Strain rate. For example, we can do deformation of a particular material by forging operation. This is my material. I am very slowly apply a compressive force onto this material. At that time, the strain rate is very low. Very low. Strain rate is very low. But when I do the strain deformation by hammering, I am doing hammering on this object. Hammering means we apply the force at a very high speed, so that the strain rate will be very higher in case of hammering. Okay. So this strain rate is very important, which affect the metal flow. If the strain rate is very low, we can deform the material to very large extent, okay, without any fracture, and that is called superplasticity of the material. You may study superplasticity in the metallurgy and material science class. If we reduce the strain rate into very low value, that means the deformation in very low rate, we apply the deformation force in very low rate, the straining or deformation is in very low rate, then we can deform the material to very large extent. Even 2000 times reduction is possible with a very low strain rate. So strain rate is a factor which affects the plastic deformation. And if we increase the strain rate, of course, the difficulty will increase for yielding or plastic deformation. So the ductility is the main factor. If we reduce the strain rate, we can increase the ductility to very large extent. But this strain rate is actually depend on the temperature. Okay, the influence of the strain rate is directly dependent upon the temperature. Here in this graph, we can see at a higher temperature. See the temperature, 1000 degrees Celsius. Under very high temperature, the influence, this is the tensile strength or yield strength. We can give the yield strength. Okay, yield strength required for plastic deformation. Under very high temperature, the strain rate has a very high influence on the yield strength. We can see the variation of the strain rate. It's a steep variation. So, higher temperature is the main agent which influence strain rate on the yield strength of the material. But here we can see the low temperature, 30 degrees Celsius. When we increase the strain rate, this is an increase of strain rate. When we increase the strain rate, it has low effect on the yield strength of the material. So that is another factor, temperature, which affect the strain rate, and strain rate which affect the yield strength of the material. And in metal flow, that is a non-steady state flow. That means there will be some, the contact is not perfect. Every time there will not be any contact between the die and the workpiece. Here, in this time, this is the contact, but after deformation, the contact area will be different. Okay, so with respect to time, this deformation, the metal flow will be different. Okay, so that we can say this is a non-steady state. So since the contact and temperature is very important, the length of contact time and the nature of heat transfer is influence temperature very significantly. Because if there is a contact, then there will be some dissipation of the generated heat into the die and the atmosphere. If the contact space is very less, then the dissipation will be lower. So this contact time is very important. We know when you touch on the very hot surface for a long time, the heat transfer will be very high. But when just touch and remove the hand, then the heat transfer is very low. So same thing is applicable here. If the contact length is very high, then the heat transfer will be large between the die and the workpiece. Okay. So that is this is upsetting process by forging. So here this contact time is important, which affect the temperature. So this is another case. The contact time under pressure between the deformed material and the die is most significant factor influencing the temperature condition. So the contact time is important, and the pressure also, pressure between the die and the workpiece. If the pressure is really low, then there will not be any perfect contact between the workpiece and the die. At the same time, the contact time also an important factor which affect the influence the temperature conditions. And here we can see a curve. This is the curve of forging with respect to, so I am doing a 3 forging. First one is a pressing forging, and this graph showing hydraulic press. This is the graph showing hydraulic press. Okay, and another graph, the dotted one. This is the graph showing drop hammer. That means using a hammer, drop hammer. A impact load is applied on the material. Okay, and another we have another curve here also. That is a screw press, using screw press. So when we use 3 machines for the forging of the same material, we can see the strain rate and the temperature effects for the same forging process different. Because if we supply the impact load, the strain rate is different. If we supply a press forging or hydraulic forging, then the strain rate is different. So in each machine, the strain rate is different. So this strain rate actually affect the temperature also. So this strain rate and the temperature also affect the metal flow. Okay. So in hot forging, not only the material and formed shape, but also the type of equipment used, the rate of deformation, that is the strain rate, chilling effects determine the metal flow behavior for load and energy requirement in the process. So So this is the distribution of temperature for a material during the forging process. This is the material. This is the material. This one is the die. Okay. So the temperature distribution at the end of TI64 cylinder offset test is shown here. The dimension of the cylinder is 1 inch. Diameter is given, and temperature of the cylinder in starting before deformation temperature was 955 degrees Celsius. 955 degrees Celsius. Starting die temperature. Starting die temperature before deformation, the temperature was 150 degrees Celsius for the die. Okay, and then after performed the reduction, so this workpiece is reduced to lower height, 50% reduction. 50% reduction. That means, for example, initial height was 100 for this workpiece. If it is 100, then after deformation, the height is reduced to 50. After 50% reduction, we can see the variation of temperature. The temperature is the temperature range for the pancake at the end of upsetting. So that means in this region, the temperature is around, initially it was 955 degrees Celsius, but after reduction in this region, the temperature is increased to 990 degrees Celsius. 990 degrees Celsius. And what about the die? Initially it was 150, but is increased to 385. By the heat transfer from the workpiece into die, the temperature of the die increased from 150 to 385, and the temperature of the workpiece is increased from 955. It's a hot forging. Temperature is 955 to 990 degrees Celsius. So there will be a temperature increase in the die as well as the material. I already explained what is the sources of this heat. So that is about this metal forming area. So in this metal forming, I explained this area. What about the plastic deformation, stress strain relationship, yield criteria, flow rule, power energy deformation, heat generation, temperature and forging. And next class we will discuss about the rolling process. This is the rolling process. Okay, so one type of metal or plastic deformation process. So I concluding this lecture. Thank you everyone.